electric potential and potential difference. So far we've talked about electric potential energy, the potential energy that a charge will have in an electric field. We're now going to define a new term, even though we've used the term voltage before. This new term is called electric potential, not potential energy, but electric potential. And it represents the amount of energy a charge will have in an electric field, or due to this conservative force, per charge. So energy per charge, the units are volts. So again, if we have a change in potential energy, we can equate that to a change in electric potential. We can flip that around also and say that if there's a potential difference, if there's a voltage difference between 2 points in space, a charge of Q will experience a change in potential energy of delta U as it goes from one point to the other point. So anytime we have a potential difference, we usually refer to that in terms of volts. Volts are joules per coulomb. Now, potential difference, the potential difference between 2 points, okay, could be the potential difference between the positive and negative terminal on a battery, could be the potential difference between the hot and the neutral in AC, alternating current electricity. But basically, the difference in potential at these 2 points can be seen as the integral of the electric field dot some infinitesimal path that we travel. If we want to eliminate the dot product right here, we can rewrite this as the scalar magnitude of the electric field times some infinitesimal path times cosine theta. And the theta just represents if there's a difference in the angle between where the electric field is pointing and the path that we're traveling. Remember, we're going from one point to another point. This is a fairly complicated integral for many cases, because our electric field will actually depend oftentimes on on direction and some other things. But if we go back to our parallel plate capacitor, we'll actually see that looking at the potential difference and looking at the electric field, it really simplifies a lot, and we don't have to worry about the calculus. We can use algebra. Now again, let's just try to use our gravity analogy. When we're looking at a mass moving in a gravitational field or falling in a gravitational field, we talk about the strength of the gravitational field related to g, the acceleration of gravity. Okay? As it moves with the gravitational field, it converts potential energy into kinetic energy. We can say the same for a positive charge moving in an electric field, which is going from a higher electric potential to a lower electric potential. A higher voltage to a lower voltage, that is analogous to a mass going from a higher altitude to a lower altitude. So again, think of this analogy of something at the top of the hill rolling down to the bottom of the hill. We want to go from higher altitude to lower altitude, to go from a higher potential energy to a lower potential energy. The same thing is true with a positive charge. It will tend to go from a higher voltage to a lower voltage. Here's an example of using an electric potential to put energy into a particular system. Now, while positive charges like to go from higher voltage to lower voltage, negative charges, we reverse this. Okay? So in this case, this is a cathode ray tube, the old way that we used to make televisions. And there would be a heating element at the back end. This would be the cathode. It would be the source of the electrons. The filament would heat up. It's no different from an incandescent light filament. It's made of tungsten. It would get hot, and as it got hotter, give enough energy to the electrons to break free of what's called the work function of the metal. Once these electrons are free, the negative charge over here, the negative voltage over here, would repel the electrons, and the positive voltage on these anodes would pull the electrons toward them. So once again, we're adding energy to these electrons. They leave the filament, they have a higher potential energy and a lower potential energy. That potential energy is turned into kinetic energy that accelerates the electron beam. The electron beam hits a fluorescent screen the screen is phosphorus, and that'll convert the energy from the electron, the kinetic energy from the electron, into luminous energy. Now, the way that this would work is you'd have these accelerating anodes, but you'd also have steering anodes, which would direct this beam across the screen. In 1/60th of a second, this beam would have traced its way all the way across the screen, and depending on the current right here, you could actually adjust the current of how many electrons were going through. You could actually paint an image. Now, black and white televisions were easy. Color televisions, you actually had to use 3 of these cathode ray setups, and they would actually shadow for each color, red, green, and blue, such that one electron beam could only hit red pixels, one electron beam could only hit green pixels, and one electron beam could only hit blue pixels. And this was a technology that we used for televisions for quite some time. Here is a particle accelerator, and it actually works. You know, we think of particle accelerator, we think of very sophisticated devices where we're accelerating particles such as protons to very, very high speeds, nearly to the speed of light. But in actuality, they're not as complicated as one might think. At the proton source, we actually have a Van de Graaff generator. It produces a high voltage. This high voltage will then be used to push or accelerate whatever particle that we want to accelerate. In this case, we're taking a proton, could just be a single ionized hydrogen atom. You can also do the same thing with heavier ions. But the proton is injected into this little microwave cavity right here. And later on we'll see that microwaves are actually oscillating electromagnetic waves. The microwaves have their electric field pointing in the positive x direction during one phase, and then they oscillate to point in the negative x direction during the off phase. So the proton comes in, it feels the on phase of the microwave, pointing it down the channel, okay? Then it enters these drift tubes. Now the drift tubes are basically little Faraday cages. Remember from the previous chapter that you can't have an electric field inside a conductor? So the proton will hide in one of these drift tubes while the microwaves are pointing in the wrong direction, and then emerge out there and feel another acceleration. So in between the drift tubes, this proton is getting another kick to go faster and faster and faster, where every time our microwaves are pointing in the positive x direction, there's a potential difference between one end of the tube and another end of the tube. And that gives the proton, whatever particle we're accelerating, more and more kinetic energy as it goes down the beam. And again, this is an actual view of one of the linear particle accelerators, and you can see what we have here is we actually have little openings where the microwaves would be sent into the chamber itself, and then you have the little drift tubes right here which hang there. So made of copper, because it's a very good conductor. That would be part of the channel that you might see in a particle accelerator. Now let's talk about something that we all use, and those are batteries. These are actually carbon batteries. These are dry cells that are often used, and they come in a variety of different sizes. Here you have your big D battery, a C, AA, AAA, and here you have your 9-volt right here. These use chemical energy or chemical potential energy to turn it into an electric potential, and then that can be used to do work on some moving charge. Now these are all rated by 1.5 volts, which means that any charge that is hooked up to this, if it goes from the positive terminal to the negative terminal, and the negative terminal to the positive terminal, depending on its charge, it will receive 1.5 joules for every coulomb of charge that moves. Now, the bigger cells actually contain more energy, and essentially we can think of these dry cells as containing a lot of different ions, and with more ions for a given voltage you have more energy stored within these. But again, these provide an electric potential difference to power whatever device that you want to use. Bigger batteries, such as car batteries, again, just think of it as a bigger container of ions. Ions have charge as they move. This is a 12-volt battery. For every coulomb of charge that we move through here, we will get 12 joules of work from this, or be able to use 12 joules of electrical energy. This lead-acid battery at 12 volts is actually 6 galvanic cells put together. These are 6 electrochemical cells put together. They're put in series. So you get 2 volts from the first set, 2 volts from the second set, 2 volts from the next set. 2 times 6 gives you 12, and that's why these batteries, these lead-acid batteries, are rated for 12 volts. The electric car. Tesla is very famous for really bringing the electric car to the mainstream. There have been electric cars in the past, but Tesla, of course, has been one of the most successful of these companies. And these involve a tremendous amount of energy to keep this car going. You know, I don't know what they're rated for. They're probably rated for about 300 miles. That requires a tremendous amount of mechanical work to keep the car going that far. So you need a tremendous amount of electric potential energy. And what Tesla does, and many of the car manufacturers have different geometries that they use. Some use the Tesla geometry. What they'll do is create these smaller lithium-ion batteries. These lithium-ion batteries each have a voltage of about 3.6 volts. And they'll put many of them in series and many of them in parallel. So you have this huge battery bank that the whole car is sitting on, which converts chemical energy into electric potential energy. That electric potential energy is then used to power the motors. They convert the electrical energy into mechanical energy. Okay? And actually, many of these banks are put in parallel, so you have a lot of smaller batteries all working together at the same voltage, and then we put them in series. So, you know, typically you might have the whole car powered by a few hundred volts, in fact. And the higher voltage can be a little bit dangerous. You know, whenever operating on or working on any of these cars, you've got to be very careful to make sure that you're not working with any live voltage. But again, basically we plug these in, we use electrical energy to store the chemical energy. The chemical energy can be used again to create electrical energy and do work and power the whole car. Your own home has electrical power, but this is alternating current, unlike the DC electricity that we get from a battery. Now, DC means direct. The electricity only flows in one direction. Going back to this, we have a positive terminal and a negative terminal. The electricity flows from the positive terminal to the negative terminal. Obviously, there's going to be something in between. We don't want to short it out. But it only flows in one direction. Well, you charge it, it actually flows in the other direction. But when we're using the energy from the battery, it's in one direction. Same thing with the electric car. The energy is flowing, the electricity is flowing in one direction. There's a positive terminal, there's a negative terminal. With alternating current, it actually oscillates in polarity, which means that when we plug something in, there's a hot terminal and there's a neutral terminal. The neutral terminal is always said to be at 0 volts, no electric potential. The hot terminal, however, oscillates from a positive voltage to a negative voltage. It produces a sinusoidal voltage, and we know that sine oscillates from positive 1 to negative 1. This actually oscillates from about positive 170 volts to negative 170 volts. We often refer to this as 120 or 110 volt. That number there is actually the root mean squared voltage. If you were to take the sine function and you were to integrate over the voltage over time and look at the root mean squared number, that's the figure that you would get. Higher voltage is also available, 240 volts, but again, this is oscillating. So we look at our direct current. Again, direct current, usually what we get from a battery, usually what a computer or digital device will operate on. There's a positive terminal, there's a negative terminal. AC, alternating. We'll talk about this later on when we get into alternating current in a later chapter. USB, we're probably all familiar with USB. USB is a serial standard. It is a type of port that is not only used to send data, it's actually used to send power. Now, the data is sent by high and low voltages, but you can also power devices with this, and it powers at about 5 volts. So when you plug something in, not only can you communicate from one device to another device, if you want to charge that particular device, say a cell phone, you're also charging with direct current at about 5 volts. So again, potential energy, potential. Potential energy, as its name implies, is energy. It's measured in joules. Potential is how much energy we get for the amount of charge that we send. And again, when we're looking at energy and potential, if we're going from a higher voltage to a lower voltage, positive charges will lose potential energy and they will convert that into some other form. For an electron, electrons like to go against the field, so they lose potential energy going from a negative voltage to a positive voltage. So once again, positive charge, when placed in an electric field, likes to move in the direction of the field because that's sort of downhill for it, if you will. That is where the energy, the electric potential energy, is going to decrease. For the electron, it's obviously the opposite. Oftentimes, this electric potential energy is turned into other forms of energy. If the charge is just allowed to accelerate, it just simply becomes kinetic energy. But oftentimes, we use this potential energy to do something. Maybe we hook it up to an LED to create light from this potential energy. Maybe we hook it up to a motor to convert the potential energy into mechanical work. And again, here's an example of a positive charge. A positive charge will move from a positive voltage to a negative voltage. We reverse the polarity. A negative particle, such as an electron, will go from a negative voltage to a positive voltage. Let's do a calculation right here. We have a proton. It's released at rest, just like we had in the previous example, at -2 centimeters, and it moves to 5 centimeters. This is an earlier problem that we did in the previous case. We want to calculate what the change in voltage is. We've already calculated the change in potential energy. Once again, electric potential is the amount of energy we get per unit charge. So if we know our change in potential energy, calculate